Good afternoon, everyone, and welcome to today's EOL seminar. I am Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Arias Hernandez. Dr. Hernandez is originally from Colombia, where he did his undergraduate studies in mathematics and electronics engineering. He received his PhD in electrical engineering from Colorado State University in 2023. During his PhD, he worked with dual polarimetric weather radars and participated in many international field campaigns, including the RELAMPAGO field campaign in 2018. In 2021, Ivan visited EOL and worked on creating the radar methodology for the RELAMPAGO domain in Argentina. Currently, Ivan is the lead operator, engineer, and data mentor of the CSU Chivo C-band radar. Please join me in welcoming Dr. Hernandez for his seminar titled Insight into the Microphysics of Severe Storms from Multiple Radar Observations, Study over the Plata region in South America. As a reminder for those of you online, please feel free to submit your questions in Slido at the bottom of your screen, and we will take them at the end of the seminar. Thanks.
Well, thanks for the invitation to give a seminar today. So this seminar is some of the work that I did during my PhD in CSU. And I would like to thank my advisor, Professor B. Sekar. And this work is over the RELAMPAGO domain in Argentina. And I'm showing some of the radar data analysis that I did with all the radar that we sent to Argentina. So this is some of the background for today, or the outlines for today. Then let me start with some of the motivation for my study. So in November 2018, we sent this radar, the CSU Chivo radar, which is a C-band radar, to Argentina, and during the RELAMPAGO campaign. And then this region, Argentina, is known for some of the severe storms in the world. So we sent the CSU Chivo radar, which is near the in the I-25 north, I guess, near the Budweiser brewery, kind of in front. So we took it to Argentina, we deployed it there, and we got a pretty interesting data set. You can see here one of the RHIs reaching almost 20 kilometers, and pretty core of like high reflectivity. And we observed a lot of help on the ground too, and a lot of health reports. In addition to the radar that we brought to Argentina, we also have satellite observations. So I guess I was trying to combine all of them to know more about the microphysics of severe weather. And that's what I'm showing today. So this region, the RELAMPAGO region where we took data from Argentina, is known for having some of the tallest storms in the world based on satellite observation. And then tallest storm means, right, we have more deep convection in that area. So we send the Chivo radar, but also the DOEs and the self-calibrate radar, the ARM facility down there. And here is a map with the geometry of these, where these two radars were located. So it's at the Sierra de Córdoba, which is like one of the terrains there, kind of the foothills of the Andes. And then the self-calibrate was kind of close to the terrain. And then the Chivo radar was more like in the plains. And then the operational radar was in the Córdoba city, which is also a C-band radar. So one of the things I did, because we have one of the tallest storms, then I said, okay, I'm going to take a look at the ecotops first and see if we actually get this very tall storm. For sure, we got few cases. So here is the ecotop height, and then the times of the radar were in the RELAMPAGO domain or in Argentina. And then I put here this line is the prevalent tropopause in summer in that region. And then you can see like quite a bit of storm naked over the profiles. So today I'm using this case. This is the December 14, 2018 case. This is mainly the case that I analyze in detail, and then I try to combine all this information from the radars and use to give a little bit of background of the radar measurement that I'm using the reflectivity, differential reflectivity, the color correlation, the phase, and specific differential phase, and then I did some work on computing the attenuation in deep convection, especially melting ice with the C-band radars. So here, probably keep in mind, so this is the way I compute attenuation using the PDP algorithm, and then later I will refer about this alpha coefficient, which is basically the attenuation coefficient for the C-band radar to compute attenuation and correct for attenuation. One of the things, so GPM make some good overpasses during the RELAMPAGO campaign too. So here is one of the overpasses, but in total we have probably 5 overpasses with deep convection happening in this region. So I was trying to combine, then we have these 3 radars. We have the CSU radar, the C-sample radar, and then the operational radar. They were 3 working at the same band, like the C-band, and they collect data for simultaneous data during the time that RELAMPAGO was happening, and then also we have other passes of GPM, and then I was trying to combine them to kind of learn more about the microphysics of this storm. Then here I'm showing like an RHI from the Chivo radar, and then an overpass from GPM for this case, and you could see, well, the melting layer kind of coincides, and the storm seems to be like a similar height. So by kind of want to do like more quantitative comparison between these radar. So I use this volume matching method that was developed previously at CSU, and this method, what it does is compute what are the common values between a moving platform and a ground radar, and then in this common volume, then you can compute like what is the reflectivity for each radar, and then compare it like more quantitatively. And that's what I did for one of the cases during one of the passes that was from GPM that was overlapping with the Chivo radar. And then here I'm comparing the KU band reflectivity with the reflectivity from the Chivo radar. And you can see that like higher reflectivity can start deviating the 1-to-1 line from GPM and the Chivo radar. And so I was wondering why, and then this reflectivity was after attenuation correction from both radars. So what I did was, okay, I'm using the attenuation correction kind of coefficients that are kind of used globally, computed from kind of global kind of drop size distribution. So what I did was, okay, we have also this barometer during the RELAMPAGO campaign, so I did some scattering simulations, and then I got like what are the exactly attenuation correction coefficients, and then I recompute the whole volume matching and then compare them, and then now they match pretty well between the Chivo radar and the DPR radar. So the thing here is like the drop side distribution in this region of Argentina is probably playing a role in the type of attenuation we are having. So I did this comparison after using the attenuation correction coefficients from the RELAMPAGO domain Then I did attenuation correction, and I compare each pair of radar. So I basically compare each of the ground radar between them, and then also each of the ground radar between them and GPM. So, and then I got this table, which are kind of hard to interpret. So I put it in this figure here, kind of like vectors going or in a pyramid way. Basically, this figure here shows in parentheses what is the bias between one of the radar to the other, and then in brackets it shows the correlation between the two reflectivities from the simultaneous cases that we have during the RELAMPAGO campaign. And then one of the questions I was asking is, okay, are these numbers make sense? Like, is there a way to make sense of these bias and see if these bias are consistent between them? So one thing I noticed is like, okay, if we have the bias between like one phase of this pyramid, basically if you go from Chivo again to Chivo, like if you start adding all these bias between them, it's like the bias around, if you go around one of the faces of this pyramid should be zero, because at the end you are going back to the same instrument. So that's what I did. So basically, when I add the bias between, I guess, Chivo to GPM, DPM to operational radar, and then going back to Chivo again, then I compute what I call the differential bias, going through the network of radar, and then I guess this differential bias should be zero, because at the end I'm going back to the same radar. But yeah, we still have like half of dB kind of different. So I was trying to get a more consistent bias using the correlation. Basically, what I did was, okay, I know the bias between Chivo and C-Sapper is going directly is 1.31, but if I go around, like if I go from Chivo to the operational radar back to C-Sapper, then the bias that I get is less than this one, but still I probably feel more confident about this bias because the correlation is higher than going from one radar to the other. But then I can also go from Chivo to C-Sapper to GPM, then in that way the bias is also lower. But so this lower bias kind of like is indicating that probably this bias is lower than 1.3 dB, but still I trust more this bias because it has a higher correlation. So then I kind of did like an average using the correlation as a weighting function, or as a weight to this average. Basically, I compute the bias, like a more consistent bias between each instrument, using the correlation as a weight. And then after doing that, then you can see if I go around one of the faces of this pyramid, then I get like the differential bias reduces to a fraction of a dB. So then I feel more confident on this bias, like what is exactly the bias between one radar to the other in a network kind of environment. So this bias is kind of tied to the other instrument. So that gives me more confident on what is the bias exactly between one radar to the other. So this was kind of like a preliminary thing, kind of like to find the bias between the radars in the network, and getting like a good quality of data to kind of conduct my microphysics experiments or analysis. And then in addition to this GPM bias and network and bias kind of in a network, I also did some pointing angle calibration and some CDR calibration and self-consistency and RCA for this network radar data set. And then after that, then I started doing all my retrievals like frame rates and ecotopes and all these, after doing all these data quality. So one of the things I did here at NCAR during my graduate visiting with Tommy was we were combining the radar retrievals from the radars in the network. In this case, so this plot here shows the coverage of each of the radars, and then I guess what I tried to combine was the run rate and the echo tops and the hail detection. And I was trying to think, okay, what's a smart way to combine these retrievals from different radars? And this is again after doing all these bias, so I was pretty confident on okay, I really account for the bias, I really account for the CDR, and so I was pretty confident on the data at this point to kind of okay, if I want to merge them, then how can I do that? So this is an example for the December 14 case, and this is the accumulated rain for this event. And this is the rain accumulation for the Chivo radar, for the directional radar, and for the C-Southern radar. And this rain accumulation is done using the lowest elevation angle. And then the lowest elevation angles are always challenging to use because you have blockage or you can have interference. You can have terrain blockage or vegetation that also blockage. And that is the case here in the CSU Chivo radar. We can see here it's pretty clear that we have a blockage here, and that comes from the vegetation that was around where the Chivo radar was installed. Then from the RMA, we can see these artifacts here that were probably coming from radio frequency interference because the radar was in the middle of the cities and it was getting a lot of interference from other sources. And then the C-Southern radar also have the Sierras, like it was right at the foothills, so have blockage from the terrain. So I was trying to combine these three rain maps using these, like taking into account that the radars have some blockage, has interference. So I basically remove what I like this part from the Chivo radar, and in this part I use what was observed by the operational radar and the C-Southern radar, and also remove, like I identify where the main sources of errors were coming, and then this is the end product after combining them. So you could see now combining the information from all these three radars now have a better coverage from the rain, and also we average the two radars or the three radars where we have information available, but when we don't have or we didn't feel confident about the information from one particular part of the radar, so we just use the other two radars to complement. So in this way, we create a bigger map, and then I did it also for echo tops and then hail detection, and then yeah, I'm not showing that here today, but I'm trying to find like connections between radar echo tops and rain rates and hail detection for these deep convective cases. So yeah. So one thing I noticed when I was computing the rain rates was that, yeah, even like, I noticed like a big difference for some cases in the rain between the Chivo and the C-Southern radar. For example, in this case, we have a square line between the Chivo radar, and the Chivo radar is the C here, and the C-Southern radar is the Y here. So you could see the rain rates were higher at the C-Southern radar than at the Chivo radar. And I think that wasn't necessarily an artifact. I think that was because the attenuation that goes after crossing this line was probably higher than what the attenuation algorithms can compensate for. So I was thinking, okay, maybe something is going on in this region here that is not letting me obtain like 100% or So that's why I'm getting a lower rain rate in this part. So yeah, for this case, so I started looking at the radar moments. So I noticed in the CDR, for example, so this is the same case. But I noticed, for example, here, so this is a CDR plot. This is from the Chivo radar, and this is from the CSAPER radar. And I center both, like the zero is at the Chivo radar, but actually the CSAPER radar is located here. But I use center both at the same time just to show the location. So I noticed like we already had values in the CDR followed by negative value, and this is like a low elevation angle. So, and then if you look at this value here in the Chivo radar, which haven't crossed these high values in CDR, these values should be positive. And something similar happened to the Chivo radar. It goes to a very high values in CDR, and then it goes like there. The differential reflectivity drops even after attenuation correction. And you can see that here, these values should be positive. So I was thinking, okay, maybe this is probably attenuation from melting ice that I'm having there. So I was curious, okay, if I'm having the attenuation from melting ice, so what should be the attenuation then that I'm having? And also I was looking for more evidence to corroborate that I have actually melting ice in this region. So I took this. So this I was taking very close to the time that I showed you before. And you could see a lot of things going in the vertical for this particular angle. So you could see, for example, there is a CDR column which is associated to updraft, and then you can see very high values in the reflectivity, and also you could see maybe an inflow or two inflows here to the CDR column. And then I ran hygrometer classification over this using these radar measurements. Then here I'm showing the hygrometer classification for this case. And then the magenta or the pink here is a mixture of rain and hail. So actually this hydroclass algorithm was developed at CSU2. Actually is identifying a melting ice or a mixed phase, at least in this region. So yeah, that's one evidence probably that I'm having probably melting ice in this region. The other thing I did was the dual Doppler winds. So I took the radar data from the CSAPER radar and the Chivo radar, and then I basically the volume scan between them for this case, and then I compute the Doppler winds using the PyDDA algorithm. And then here I'm showing, so it's the maximum reflectivity over the column, and then updraft and contours here. Yes, these are like 20 meters per second contours. So this region here is where we found the melting or the melting ice signatures, and then at this copy at the mid levels, you can see that it's even like a vortex kind of pattern. So it means like we probably have a very very strong updraft, and then we can see at this cross section here, we can see this recirculation pattern pretty clear in the Doppler winds. And this recirculation pattern is probably associated to hail growth. So we're probably having maybe hail or ice particles coming inside the updraft again and recirculating. So that's another kind of evidence. And then from the weather reports, so there were like significant amount of like heavy rain and hail reports during that day, and then this picture was taken near this region. So hail was observed on the ground too. So we think we will have a melting ice problem there. And hence attenuation from melting ice. So the question is, okay, how can I compute the attenuation from this data? So I use this network-based approach. So basically, what it does is combine the reflectivity from two radars and try to combine them optimally. And so I use the C-sub radar and Geo radar in this network algorithm, and then this is a reference for the algorithm. And then so basically this algorithm combines the two reflectivities, and it doesn't use the FDP method to compute the attenuation. It does it by matching the two radar reflectivity. So this is the array plot from the radar reflectivity at the direction that I was showing in the PPI scan. So here I'm showing in the magenta here is the measured reflectivity. And then the red here is the corrected reflectivity using the FDP method. And then when I compute the reflectivity using the network-based approach, you can see there is a big difference after 38 kilometers they start deviating, and it reached almost the 70 dBc. So basically, what it's telling me is like, okay, the network-based reflectivity is significantly higher in this region where the melting ice is. And that's probably why I was seeing these signatures in the CDR. So what I did was I started increasing, and this is the attenuation equation where you have the alpha value, which is the attenuation correction coefficient that you use to correct or to account for attenuation. So what I did was I identified based on the polarimetric measurements where it was exactly the melting ice region using the CDR and the ROHV, and then the difference between the network reflectivity minus the corrected reflectivity. And you can see here the differential reflectivity start kind of taking off after 37 kilometers and then kind of stabilize again after 42 kilometers. In the same way, the ROHV, which is the blue line here, start dropping very significantly at the same time, and then back up again when the CDR stabilizes. So I was using these two signatures to detect where to start and where to stop the using a higher attenuation correction coefficient. So basically, I increased the attenuation coefficient to match the network-based reflectivity. And in this way, I compute what is the attenuation coefficient for melting ice. And then I did it for few cases. So it was hard to identify exactly where the melting ice were. So it was kind of like a manual, but still I found like 7 parts in the data that has melting ice. So I did it for this case, and then I compute. So here is this diagram here. It shows what are the coefficients that I found for melting ice, and the bar here shows what were those coefficients from simulations. So in this paper here in risk of 2013, they basically they use scattering simulations to compute what would be the attenuation coefficient for melting ice. So I guess this is probably the first time that the attenuation for melting ice are computed in an observational or in an experimental way, and thus even there are 7 only cases that I found, but still I guess it compared well with the simulations too, and it's experimental retrieval from this. So yeah, that's after doing this, then I already know that, okay, there is something going on. I already know where these melting ice were located based on my analysis. So I thought, okay, if I know where these melting ice are, we collected I and Q in phase and quadrature time series samples during the RELAMPAGO campaign. So I thought, okay, it's probably worth it to take a look at these spectra and see if they have any special signature that I can use to understand more about the microphysics that is happening in this storm. So yeah, so this is again the chart that I showed before. So yeah, we have the CDR column again, and then I'm showing here the Doppler velocity for this case, and we can see that we have the storm was moving towards the radar, and that's why we have these negative colors. But we can see from the RHI that the storm is moving from the radar. The radar is it's located here. The storm is moving towards the radar, but this positive velocity here means probably that this recirculation pattern or the shear probably bringing this inflow of ice into this region, which is the CDR column, which probably we have the main updraft going on there. So I just draw these lines here, kind of following this positive velocity. Probably give me a clue where things are going, and will give me more ideas when I take a look at the spectrum, because the spectrum is basically a composition in the Doppler velocity of the radar measurements. So yeah, and we know from the literature that like the way CDR columns kind of form is probably having this recirculation of particles. And we can see in this case that it's not straightforward, that the particles go down, they kind of go everywhere in the updraft, and they follow different trajectories depending on how heavy they are, or the updraft, or how fast they are going. So yeah, that's why I do these lines here to represent this. And anyways, just keep in mind, like, negative velocity where towards the radar, and the positive velocity is where I think the inflows are coming into, or the ice is coming. So here, yeah, I'm drawing basically. So it's plot here to the reflectivity, and then the arrows are following the trajectories that I think where the hell is coming to the storm. And then these contours here are CDR contours. So this is where the CDR is located. And then what I did was I compute the spectra, the Doppler spectra from the IMQ data along this region, which is kind of crossing the CDR column and passing through this trajectory of hell. And that's what I'm showing next. So here I'm showing so the dual spectra, which basically is the composition of the reflectivity and the differential reflectivity and the copolar correlation along this radar beam. So basically, and here I forget to put it, but the x-axis here is the Doppler velocity, and then the y-axis is the range, and then the color means the intensity of, in this case, reflectivity or differential reflectivity or copolar correlation. And then again, this beam is crossing this, like the lower part. So because it's kind of low, it's kind of telling me more like about the vertical, or not the vertical, the horizontal motion of the storm. And the interesting part of this spectra, you could see here in the reflectivity, yeah, we have negative velocity, which means, yeah, the storm is moving towards the radar, which what we expect, but then we can see from probably 38 kilometers, which was where we identify melting ice, we could see a bimodality in the spectrum, which means there are something else moving at a different velocity. and it's more clear after 40 kilometers here that we have this, the spectrum start going higher in the reflectivity, in the positive velocity, which means something is moving away from the radar. And I think it's probably this recirculation of ice particles here that are probably crossing the updraft, but then some particles get a vector into the updraft, but I guess the heavier one keep their trajectory, and those trajectories is away from the radar, and that's why we are having this positive component in addition to the main component, which I think is coming from the rain. At the same time, I computed the CDR spectrum and the ROHV spectrum. And you can see in the CDR spectrum that the positive component, which is what I think was the ice particle crossing the storm, you could see there is very high values in the differential reflectivity spectrum, and then which these high values are associated to melting ice in the literature for zero and radar, like this hotspot in CDR that are associated to hail and ice in the C1, and then you could see the ROHV is low in this part of the spectrum. So here I'm showing a profile of the spectrum around at 40 kilometers. Basically, I'm showing the values at 40 kilometers of the reflectivity, the differential reflectivity, and the cohort correlation. That's what I'm showing here in this plot, and you can see the bimodality, like these two particles moving at different velocity, which I think probably the negative velocity were associated to rain moving towards the radar, and then the positive velocity are probably the hail that are ingested into the updraft that keep their trajectory because they were probably more heavy, and then the black here shows the CDR spectrum, which so we can see like a CDR around 1 dB, which is probably more reasonable for rain, and you can see the other part of the spectrum, which is lower, but it has a very high values of differential reflectivity, which is probably associated to melting ice. And then the ROHV also drop in this part, which is probably mean there are more like different shapes going on in this part of the spectrum. So I associate this part of the spectrum to the rain, and this part of the spectrum to the melting ice. But I still one of the question I have is this big difference, like almost 30 dB difference between rain and melting ice, and normally melting ice or hail are bigger, so I was expecting probably a higher return. But I think it's probably due to maybe there is not a lot of melting ice in this region, and that's why we don't see a huge return in the differential reflectivity, but still we can see a signature there. See that. I guess some of my summary. So I use this network of radar with the RELAMPAGO campaign to learn more about the microphysics of these storms. I did cross validation with GPM, and then I compared all this radar, and then I found a self-calibrated method to find a consistent bias in between a radar network. I combined radar retrievals in using the best characteristic of each radar to combine and get better retrievals in a radar network. And I also studied attenuation of melting ice using this network of radars. And I think perhaps this is the first time like the attenuation correction coefficients for melting ice are computed from observations. And then finally, I study the spectral polarimetric to understand more about the microphysics in updraft environments. Yeah. Thank you. Some reference. Oh yeah, some future work. I guess some of the things that I'm working now is doing some scattering simulations on melting ice to support some of this experimental work for the attenuation component. And I also analyzing more cases during the RELAMPAGO campaign that also has signatures of melting ice, and I also have IQ data that I'm checking and see how we can use the INQ spectra to learn more about the microphysics of updraft. And also I want to use more GPM data with some of the pros that GPM has for the microphysics and compare it with the radar. And yeah, so some of the reference for today. Yeah, thanks.
Thanks, Evan, for that very interesting seminar. As a reminder for those online, feel free to submit your questions on Slido. Do we have any questions from the room?
Nice presentation. Comparing with the C-band, which is 5 gigahertz, and GPM-KU about double the frequency.
Yeah.
Could you comment on knee scattering issues between those two frequencies? Because wondering, you got a very good bias correction or lower bias between those two radars of attenuation correction. I was wondering about other knee scattering.
Yeah, so let me go back to this slide here. Yeah, so for the like you're right, like the mean scattering could happen more frequently when you're going higher in frequency. And there is this study from Biswash and Chandrasekhar. They did some simulations on like with different hydrometers, and then they found that the radar reflectivity is lower than 50 dBc. Still give you a good comparison between the two frequencies. So that's why I'm probably cutting here below the 45 dBc. So I'm using kind of like not like a big range in dB. So I'm using until probably 45 dBc to compare these two radar. But yeah, you are right. There might be bias induced by mean scattering.
Sure. Yeah. My suggestion is, the GPM has two frequencies, KU and KA band. They also produce the attenuation correction with those two. I was wondering whether you had a chance to look at that attenuation, what they come with the KU and the KA band, then that could be related to your C band attenuation. That's maybe you have to look at it. Maybe in the future you can look at that also.
Yeah, that's a good idea. Definitely. Thanks.
There was an Austral. When you showed that Doppler example, was the last slide. Back on here. When I looked at that from an expert in vertically pointing radar, I would have thought that was an artifact. How confident that up and down motion you're seeing is not some kind of spectral artifact, because you get a very strong signal there. When we look at vertically pointing radars, it often produces kind of a mirror image that is clearly an artifact.
So I thought about it. Like, is it second trip or is I don't know, three-body scattering or something like that. So I think it's legit data. So because it's in the other direction that is happening. So it's in a positive direction, and I think it's kind of consistent with like having some positive velocity to happening in the vertical. So I think there are particles that were moving in a positive velocity in this region. And the other signatures, like having like very high CDR, is also associated to melting ice. So it's a pretty clear signature. So I was expecting if it was an artifact or a second tape, I would get a different kind of or a different kind of.
But I wasn't thinking it was Stephen Trap, it was more some kind of spectral processing.
Like from silos and stuff.
Maybe.
Yeah, but still is something that I'm. So this is the data, and I'm still trying to figure out what are these signatures, exactly. So this is my explanation to it. It's probably melting ice, but yeah.
Thanks, Ivan.
Oh,
It's a really interesting seminar.
Jimmy, I tuned it.
Oh, it's off. Thanks, Ivan. Really interesting seminar. Great job. So about this same topic, is this perhaps in the region where you were able to do a dual Doppler retrieval?
Yeah.
So that could also help to
Mm-hmm.
to confirm or deny the
Yeah.
accuracy of that
Yeah. So
pair of up-down region. So what, in your dual Doppler retrieval, what was the maximum updraft that you did observe?
yeah. So for this one, I got 40 meters per second, and I don't have the sounding here, but the theoretical kind of maximum updraft was 60 meters per second based on the K for this case. So still reasonable, maybe. Yeah, it was probably like a real updraft. Having 40, it was possible to have 40 meters per second updraft. Yeah.
Yvonne, thank you so much for a very nice talk. I was just wondering, for your dual Doppler analysis, you mentioned that you use like PyDDA to retrieve the wind field, and I was wondering, like, do you know if they consider the lower boundary condition? Like, what is their lower boundary condition? Do they consider the topography?
Mm-hmm.
Oh, okay.
Yeah, I use the mass continuity equation, and then they start retrieving at the very low, like the lowest elevation or the lowest copy, and then they go up. And then the assumption they make is that at the low elevation, if you have convergence, then if you have convergence in one particular gate, then it means your W or your velocity should go to the next to the next layer, and that way they compute the W velocity or the vertical component based on the
So you make kind of like outward integration?
yeah.
Oh, but do they consider like Dirichlet or like movement boundary condition or like the terrain slope?
Yeah, no, I don't. Yeah,
Oh, okay. Yeah.
they go as far.
Thank you.
I don't see any more questions online. Do we have any others in the room?
You're really talking about. So I was wondering for the dual pulse factor that you're showing through the updraft. Did you have any other tools through the updraft that you looked at? Because you really need to see how that varies with height within the updraft itself.
Yeah. So you mean like computing these along the updraft? You mean? Or?
Yeah, so looking at like the 2.5 degree tilt and then like a different tilt higher up.
Yeah. Yeah, I present this with different elevation at the AMS radar conference. So yeah, I was analyzing like how this spectra evolves along this CDR column, and I found like how this bimodality is kind of moving from positive to negative, and I'm analyzing this case and seeing what else I can understand from this spectra, along one of these trajectories. Yeah.
All right, cool. Thanks.
Any more questions in the room?
When you do load up analysis, is that a baseline is 7 kilometers or how big is that? Is that?
Yeah. So good question. So let's take up a map here. So yeah, the distance between the two radar is 76 kilometers.
Okay. That's kind of very large baseline for a good upper. Usually it's less than 40 kilometers. I don't know. I'm sure there are not challenges relating to events.
Yeah, like pre-processing the data to make it like in a way that the algorithm start making, or the Doppler will start making sense. Yeah, was I have to do a lot of pre-processing, but yeah, I guess like I was confident. Like I checked where the CDR columns or the CDR kind of values were, and then I kind of matched them with the and they kind of match with the updraft too. So yeah, there are uncertainties, but I think these updrafts were probably showing one part of the story, or the Doppler wings. Yeah.
Thanks.
Any more from the room? Allison.
So your analysis relied on instrumentation deployed by different organizations and agencies. What would be your recommendation for the future for how we deploy assets across agencies?
Yeah, so question, I guess. So I guess, well, I was involved in the RELAMPAGO planning meetings, and I remember coming here to NCAR for some of the meetings, and then also people from DOE were in the meeting. So I guess really RELAMPAGO planning and execution was a pretty good example, like working with different organizations. I guess one good thing that I remember from RELAMPAGO was like everybody was invited into the meetings, like the meetings were open, so everybody could pretty much like tune in, and some of the meetings, even like the meetings that were involved there or somewhere else, they were broadcast, and then people that couldn't attend were also kind of like contributing in the planning. And I guess I think it really helped, like having all these people sitting together and planning the mission. But I guess for example, we have the DOE, NASA, and even UL too, and CSU, and many different universities. But I guess the planning meetings and sitting everybody together, and it was really useful.
Great, thanks.
So I have a question too about your future work. You mentioned that you wanted to see more cases with more microphysical variability. Are there specific instances or cases that you're after to optimize your retrievals? And do you know if you have those in the RELAMPAGO campaign?
Yeah, so I'm going after the updraft, and it's fascinating what's happening in the updraft, I guess. And also I'm also trying to find more melting ice cases, because I guess melting ice is such an interesting particles, because they can produce the big hail that we can that impact the ground, and also like the large drop that they shed probably make the heavy precipitation that we see in deep convection. So I'm trying to identify these two, like updraft and melting ice.
Great. I have a follow-up to Sarah's question. So do you think that it's possible to use that climatology that you've developed of the echo tops and also do something similar with updraft strength for each of those storms? Can you calculate, do a Doppler retrieval for each of those storms and compare the updraft strength to the echo top heights, and then also bring in the microphysics of using the dual pole data and use some metric to quantify the microphysics and relate them all with how deep the storms are?
Yeah, I think that would be very interesting, but also challenging. Like, I think computing the Doppler winds for like systematically and kind of feel confident about the Doppler winds could be challenging. Because at least for this case, I kind of check every copy that I was putting inside the algorithm and making sure that makes sense. But I think it would be interesting to compute it, even if it's challenging. I think it's worth checking this out there and taking some of this in a statistical way.
Great, thanks, Simon. I think I speak for most of us when we say we're really interested to see what comes out of your future endeavors. So let's thank you, Yvonne, one more time.